So good evening, guys. So welcome back to the problem solving session and doubt clarification session on wastewater treatment and recycling. So we are into week 9. So let's have a quick recap about the topics which we covered in week 9. So in week 9, we looked into the tertiary or advanced treatment of wastewater. So we started with the need of those treatment, the main objective, options, and the approaches. And then we saw various kinds of tertiary treatments starting from the nutrient removal because we know that wastewater contains a lot of nutrients in the form of nitrogen, phosphorus. So we saw how to remove those things through nitrification, denitrification, ammonia process, ammonia stripping, then biological phosphorus removal, chemical precipitation, etc. And then we looked into the absorption and the ion exchange process. So its mechanism, what is the difference between physisorption and chemisorption, the different types of absorption used. And then we looked into ion exchange process, what are the different resins available, the configurations, uh, and how to regenerate those resins for reuse, and then some of the limitations of those methods. Then we looked into the membrane process, the various type of membrane process like ultrafiltration, microfiltration, nanofiltration, and reverse osmosis, the different kind of flow geometries, the configuration, and the membrane fouling in particular. And then at last we saw about the disinfection and the chemical treatment methods. So this was all about the week 9 topics. So I have some subjective and objective questions. So we'll start with some of the subjective questions. We'll solve one by one. I hope my voice is audible. So this is the first question, subjective question. So it says that a membrane filtration has an influent turbidity of 5 NTU and contains a heterotopic plate count. It is nothing but the bacterial count of 10 to the power 6 microorganisms per liter. Okay, so this is the influent 5 NTU and 10 to the power 6 microorganisms per liter. And the effluent from the membranes typically has less than 10 microorganisms per liter and turbidity of 0.2 NTU. So we have the details about the influent and the effluent from the membrane. Okay, so what is the log rejection of microorganisms under normal operation with no broken fibers? So we are considering that the membrane is intact, there are no broken fibers. So what is the log rejection of microorganisms? This is the first question. Now the second part says, if it is assumed that 6 out of 6,000 membrane fibers have been broken during operation, determine the impact on the effluent microorganisms count and turbidity. For the following analysis, neglect the water loss during blackwashing. So it also says in the second part that some portion of the membrane fibers are broken, that is 0.1%. So what will be the impact on the effluent microorganisms count and the turbidity? So go through the question once again, note down the parameters, we will solve this problem. So we will see how a few broken fibers from the membrane can impact the membrane performance. Okay, in this question. Okay, so we will solve this question now. So this is question number 1. Okay.
Sir,
Yeah.
sir, I'm unable to understand the question.
Okay. Okay, I will explain it. Just wait. Okay. So suppose uh, there is a membrane. Okay. There is a membrane, and generally we show membrane like this. Okay, like this middle portion we consider this as the membrane. So there is one influent coming. Okay, so this is the influent. I will write influent. Okay, some part will go as retentate because it will come out as it is. The it will not go through the membrane. Some part will come out as retentate, and some out will come out as permeate. So this is the main schematic of any membrane. So it is saying that the influent of the membrane has turbidity of 5 NTU. 5 NTU. Okay. This is the and the bacterial count. So we know that there are many microorganisms present in the wastewater. So suppose the bacterial count I will write as B in as 10 to the power 6 microbes per liter. So this is the influent that is coming. And what is coming out of the membrane? So T out will be 0.2 NTU. Okay, and the bacterial count B out will be suppose 10 microbes per liter. So this is what is given in the question. So we have to find out the log rejection. So whenever in the case of microorganisms, so we take the performance in terms of log rejection. Okay, so we will see how to find it out. So the first part, as it says, this is the first row. So log rejection in normal operation. Suppose the membrane is intact, there are no broken fibers in the membrane, so it is working normally. So log rejection in normal operation. So my LR will be equal to log of what is my B out divided by my B in. Since it is everything in the powers of 10, we will take the log. So that's why it is known as log rejection. So it will be log of 10 to the power 6. Oh, sorry, I have just, it will be B in by B out. Okay, 10 to the power 6 organisms per liter divided by 10 organisms per liter. So my log rejection is 5. Fine. Are you able to understand? What did we find out? Saket, is it clear? Hello, am I audible?
Sir,
Yeah.
sir, why we divide bacterial in by bacterial out?
No, we are just finding out that how much in terms of log, how much of my bacteria are getting removed. It's just a ratio, but in terms of log. Okay.
Okay, sir.
Okay, it's just a ratio, nothing else. Because since we are dealing in the powers of 10, sometimes it will be 10 to the minus, it will 10 to the 12, 10. We don't know. It is a very high number. So if we do the normal ratio, the number will be very high. It will be difficult to compare. So what we do, we convert everything in terms of log and then find the ratio. So it gives an easy picture. We will see like how if suppose in this membrane some part of it is getting damaged. So how it will affect my operation, how it will damage the system. Okay, so we'll see. So this is the first part in the normal operation. So now suppose 6 out of how many? 6,000 fibers. So the membrane fibers, there are totally 6,000 fibers are present. So 6 out of 6,000 fibers are damaged. So now what will happen? So now what will happen is that the same membrane, this is the T in that is coming and this is the B in that is coming. Okay, so this is the normal membrane. Okay, so this membrane is normal. Some part of it will go as it is, right? Because this part is not getting treated. Suppose this is the broken part. This is the broken part. Okay, so some part will get treated. So whatever will be coming out will be T out and B out. But in the broken part, there will be no change. So it will be again T in and B in, right? And suppose the final effluent that is coming out by mixing these two flows will be TE and BE. Did you get my point? So now in the membranes, totally 6,000 fibers are there. Okay, so 5,994 membranes are fine. So the your turbidity and the bacterial count will change from those things. But the six membranes which are damaged, the same concentration will come out, whatever we have put in the input. So it will be Te and B in, T in and B in. Okay, so when this both flows will come together, so at last we will get Te and Be. So we have to find out the new Te and Be. Okay, so how we will found? So now my new Be will be equal to the part which is getting removed 10 microorganisms. So how much of the percentage of flow was intact? It was 0.999 because my 99.9% flow was fine. So 0.999 plus how much was damaged? So 10 to the power 6 organisms per liter into 0.001. This was damaged and total is 1. It is same Q1 C1 plus Q2 C2 is equal to Q3 C3. That same conservation of mass formula what we are doing. And ultimately it will be 1010 organisms per liter. So this will be my uh, new plate count or new number of microorganisms. So now my log rejection in case of broken membranes will be log of 10 to the power 6 divided by 1010. So what will this be? This will be equal to 3, approximately equal to 3. So we have seen that because of six broken fibers, only 6 out of 6,000, the log rejection has been reduced from 5 to 3. So there is a drastic change in my log rejection from 5 to 3. If you see in the 10 powers of 10, so 10 to the power 5 to 10 to the power 3, like that, it has changed. So if you see my impact on turbidity, so my TE will be first the effluent turbidity from the normal membrane was zero point 0.2 into 0.999 plus the from the broken fiber was 5 MTU into 0.001 divided by 1. It will be 0.205 MTU. So you see my effluent from the normal fibers was zero point 0.2 NTU, but because of my breakage of my membranes, it has just increased to 0.205. So there is a very minute difference. Okay, so we can say that the turbidity is not changed much because of my broken fibers, but my bacterial count there is a significant reduction in the log rejection part. So this is what is matters. So we cannot, by seeing the turbidity of my effluent, we cannot say that if my water is free from bacterial count and all. So always we should do the bacterial count to find out the number of microorganisms. Is it clear? Saket, did you understand the problem now?
Yes, sir.
Okay, so this was all about. So basically, in many of the places, we take turbidity as a surrogate measure to find out the bacterial quality of the system. Sometimes we will see just the turbidity and find out and try to uh, qualitatively assess the type of wastewater. But we should not do that. From this experiment, we can find out that just by turbidity we cannot say whether the water is free from bacteria and all. Okay, so we should definitely do the bacterial count and all the microorganisms plate count to find out the true picture of the like how biologically effective it is. So this was all about the first question. Okay, so now the next question, very simple question, you can solve it in one line. So it says that a DAW FilmTech SFX membrane module, it's the name of the membrane, contains 5760 fibers, 5760 fibers, The fibers are 1.87 meter long and the outside diameter of 1.3 mm and the inside diameter is 0.7 mm. So it's a cylindrical type of membrane. Okay, so we have been given the both outside and the inside diameter. Now calculate the water production, that is nothing but the flow rate from one module if the flux is 75 liter per meter square hour. So you know the flux, like how much water is entering per meter square per hour. So we have to find the water production in two cases. One, when the flow is going from outside to inside, or when the flow is going from inside to outside. Okay, so we have to compare both the answers, like how my water production is changing or the flow rate is changing. So go through the question again. It's a very simple problem, but you can learn something from it. It's a hollow fiber membrane. So in the case of a hollow fiber membrane, the flux can be from inside to outside or outside to inside. Okay. So in both the cases, my calculation will change. We'll see how it will change. Okay. So now question number two. So suppose this is my membrane. Okay. So it has some thickness. So my outside diameter is given as 1.3 mm and my inside diameter is given as 0.7 mm. So water can flow from outside to inside. Okay, this is case number one. Or it can flow from inside to outside. Case number two. So there may be two kinds of flow possible. Okay. So suppose for outside in flow, like it is flowing from outside to inside. So what will be my area? What will be my area of in the system from in which water is flowing? Can someone tell me? Just tell me the formula. In the case of a hollow fiber membrane, what will be my area of flow? Anyone?
First, we have to find out the area of cross section, that is pi d square by 4.
No, no. See. You are saying my area of cross section. So you are saying that my water is entering from here, but that is not the case in the case of membranes, right?
Yeah, okay.
Okay. So see how I
2
have
pi
to
square h. 2 pi square h.
2 pi square h. 2 pi square h.
Sorry, pi square h.
No, pi square. From where are you getting the pi square?
No, sir. Pi r square h. Sorry.
Pi r square h. Pi r square h. Is it the surface area?
Yes, sir.
No, you just try to figure out once again. Are you telling this? I am asking about the surface area, not the volume.
That is pi into d, isn't it? That is circumference.
Yeah,
Pi
so
into
it will
pi
be
into.
it will be my circumference into length. So it will
Yeah,
be
that
pi
is pi
dl
into d into L.
L.
Yeah.
Okay, so we have to see the circumference. Suppose this is my membrane module, pi into d into the length. Okay, so my this is my surface area, the outside area, surface area. So not the volume. Pi r square will be the volume, not that. We have to see the surface area because the water will come from inside into the surface. So, but when it will be an outside inflow, I will take my diameter as outside diameter. Okay, so it will be d naught. So what will it be? So pi into 1.3 mm into 1.87 meter into 10 to the power minus 3 to meter into mm. So my area will be equal to 7.64 into 10 to the power minus 3 meter square per fiber. This is for one fiber. Okay. So what will be my water production or the flow rate? Flow rate for outside out in. Okay, outside in will be my flux J into my area. So what is my flux? Flux is 75 liter per meter square hour into area. So 7.64 into 10 to the power minus 3 meter square. So my what will be my Q in this case? It will be 3300 liter per hour. Okay. So in the case of my outside inflow, my flow rate will be 3300. Now for inside outflow, it is flowing from inside to outside. So now area will be pi b inside L. Okay. So again it will be pi into 0.7 into 1.87 into 10 to the power minus 3. So it will be 4.11 into 10 to the power minus 3 meter square per fiber. Okay, so in the last case, I didn't multiply it by the number of fibers, that is 7560. Okay, so I have to multiply by the number of fibers for the total water production. So my Q in out will be again flux into my area 4.1 into 10 to the minus 3 into the number of fibers 5760. So it will be around 1780 liter per hour. So you can see by just changing my configuration from outside in to inside out, my flow rate is becoming almost half. Okay. So this is the power of the configuration in membrane system. So if we have to control the flow rate, we can just change the configuration. Okay, so nearly double the flow rate we can get in the case of outside in. Whereas in the case of inside out, it is just half of it, half of the outside inflow. So configuration is a very important parameter in the case of membrane performance. Okay, so is it clear? Okay, so this was all about the second question. Now we'll see the third question. So these are the answers. Okay, next question. So looks a big question. We will go through it very slowly. Okay, so a treatment plant is to be designed to produce 75,700 meter cube per day of treated water at 20 degrees Celsius. So forget the temperature for now. So we have to produce this much of water, treated water. Okay. So pilot testing demonstrate that it can operate effectively at a flux of 65 liter per meter square hour. So the flow rate of the treated water is given, not the influent water. It is for the treated water. And then the flux is given with 2-minute backwash cycle for every 45 minutes of my normal operation. So we cannot operate a membrane for continuously for long time. Okay, you must have read that after some part of operation there will be maybe some fouling or some problems will be there, so we have to backwash it. So for every 45 minutes of operation there is a 2 minute of backwash. Okay, and there is a cleaning once per month. Now the membrane modules have 50 meter square of membrane area. So the for each of the membrane modules have a 50 meter square of membrane area. The pilot unit contains 3 membrane modules and a full scale rack that contain up to 100 modules. So pilot plant has just 3 membrane modules and it can be extended up to 100 modules. So, and what about backwashes? Backwashes for the pilot unit consume 300 liters of treated water. So out of whatever water is coming out from the membrane, 300 liter is required for backwashing. Also, the cleaning takes 4 hours. So cleaning takes 4 hours. Regulations require direct integrity testing, which takes 10 minutes once per day. Apart from the regular backwashing and cleaning, there is also integrity testing of the membrane, which takes 10 minutes. So we have seen 4 5 things here. One, there is a normal operation for 45 minutes. So for every 45 minutes of normal operation, there is a 2 minute of backwash. Okay. So one is the backwash thing. Other thing is the cleaning, which has to be done once per month and takes 4 hours. This is the second thing. Also, there is a regular integrity test, which take 10 minutes, which is done once per day. Okay, so apart from a normal membrane operations, three other things are also being given. So now we have to find out what is the online production factor, what is the system recovery, what is the feed flow rate, what is the total membrane area, number of racks, and number of module per racks. Okay, so there is a lot of data to confuse you, but we will go through them one by one. It will be a simple thing. Okay, so we will do this problem. Just remember that there are four different kinds of thing happening. One is the normal membrane operation. This is the first thing. Second, there is a backwashing. Third, there is a cleaning. Fourth, there is a integrity test. So we have to account time for everything. So first question that they are asking is the online production factor. So online production factor is, suppose it's a ratio. So out of the total time, how much of my time I am giving for membrane operation. Okay, so we have to find the total production factor. So suppose my total time is 1 hour. So out of 1 hour for membrane operation, how much I am giving time. Okay, so we will try to find out. Okay, so let's see. This is question number 3. So first we will see. So first case we will determine the fraction of time the membrane is operated and producing permeate. So if the membrane is operating, then only the permeate will be produced. So we will see the time factor. So first we will find the time for backwash, BW backwash. So it is 2 minutes of backwash, okay, per 45 minutes of operation. Fine. And in a day, how many minutes are there? 1440 minutes per day. Okay, so I will calculate everything in terms of per day. Okay, so 2 minutes of backwashing per 45 minutes of membrane cycle, and in a day it will be around 64 minutes per day. Fine, this is my backwash time. Now next, what is my next? Next is the integrity test, which is directly given as 10 minutes per day. So it takes 10 minutes and it has to be done once per day. So it is 10 minutes per day. And the third thing is the cleaning. Cleaning of membrane, CIP. So for it requires 4 hours. Okay. Per every month you have to do it once. So for per 30 days it requires 4 hours. And there are 60 minutes per hour. So again we will get it as 8 minutes per day. Okay, so we found out per day what is the contribution for each of the operations. So now what will be my efficiency? My efficiency will be, because I have to find total. So totally how many minutes are there in a day? 1440 minutes per day. So out of this 1440, 64 minutes is going for backwash, 10 minutes is going for integrity, and 8 minutes is going for cleaning. So it will be 0.943. So this is my online production factor. Is it clear?
Sir, this is 60 minutes per hour or 60 minutes per day?
60 minutes per hour. See, I am converting everything in terms of minute per day. Okay. So total for cleaning, it requires 4 hours per month. So it is 4 hours per 30 day. So I have to remove that hour. So for removing that hour, I multiplied with 60 minutes per hour because we know in hours 60 minutes. Okay. So I will get the answer as 8 minutes per day. Is it clear?
Okay, sir.
Yeah. So this is my online production factor, like how much fraction time my membrane is working and giving the per minute. Okay. So now I will find the system. Second question is system recovery factor. Okay. So system recovery factor means like how much of my flow is coming. Okay, suppose from the membrane I am getting 100 liters of water, but some part of my water will be used in backwashing. Suppose 2 liters is going for backwashing. So out of 100 liters, 2 liters is going for backwashing. So my system recovery factor will be 98 by 100. Okay. So we will find the system recovery factor in this case also. Okay. So we have to find, we know that 300 or rather 300 liters of water is required for backwashing. In the question it is given for 3 modules because the pilot plant has some 3 modules. Okay, and it requires 300 liters for backwashing. Okay, so per module, my backwashing requirement is 100 liters. So this is my backwashing requirement. But how much water is being produced, you have to find out. So what will be my volume of flow? How much water I am getting will be equal to flux J into the area into the time factor. Okay. So flux is given as 65 liters per meter square hour. This is the flux. What is my area? Area we know it has given as 50 meter square per module. Okay, 50 meter square. And we know that for every 45 minute of cycle, there is a 2-minute backwashing. Okay, so for every 45 minutes of cycle, there is a 2-minute backwashing. So my time factor for membrane operation directly will be 43 minutes. And I am changing minutes into hours, so 60 minutes per hour. So ultimately, it will be 2330 liters. So the volume of water that I am getting from one module is equal to 2330 liters. How I found out? I multiplied the flux into area into time because flux is liter per meter square hour. So if I multiply with some area term and some time term, this all will get cancelled. I will get the volume. Okay, so flux into area into time. So this is my total flow. So what will be my system recovery factor R? It will be 2330 minus 100 because it is used for backwashing divided by 2330. So it will be 0.957. Is it fine? So my system recovery factor is 0.957. So out of 1 meter cube of water, I am able to recover 0.975 meter cube from the membrane. The rest is going for backwashing. Okay. Also, now the third part. Third part is what is the required feed flow. So we know that the permeate flow is given as 75,700 meter cube per day. So what will be my feed flow? So my feed flow will be just my permeate flow divided by the system recovery factor. Okay, so it will be 75700 divided by 0.947. So my QF feed flow will be equal to 79,100 meter cube per day. Is it fine? So this is my feed flow. So we got the feed flow also, we have the permeate flow, we know the flux. So the fourth part, now everything will be easy. Now fourth part is total membrane area that is required. So my total membrane area required will be my QF divided by the total, how much the system is producing the flux. Okay, so by, or rather I will just write it as, so my total flow rate will be 79,000 meter cube per day. This is my total flow. Okay, so I will divide it by the flux. So that is 65 liters per meter square per hour. Abdul, I think you are unmuted. Okay. So now we have to just, but this flux is uh, operating for 0.943. We found the production factor, online production factor. So when we are finding the total area, we have to divide with the online production factor. Because for that much time only, the system is producing the permeate. So my total membrane area, I have to divide by 0.95. Rest will be my conversion factors. So it is 24 hours per day. And one more will be, in terms of liter, will be 10 to the power 3 liters per meter cube. These are my conversion factors. So my total area that is required will be 53,800 meters cube. Okay, so this is simply, we know Q is equal to flux by area. So from this, we are finding this. Okay, but I have to divide it by the online production factor, because for that much time only my system is running for producing permeate. So this is the membrane area, and fourth part, total number of modules required. So n modules will be equal to 53800 divided by 50. This is the per module membrane area. So number of modules required will be 1076. Okay, and the last part is how many racks or how many module per racks. So we have 1076 modules. Okay, and our one rack can accommodate 100 modules. So we need around 11 racks, because one rack contains around 100 modules. So now 11 racks, but this will be very packed up, like totally packed up. So instead of 11 racks, we will generally give some more spacing, and we can give, instead of 11, we can give some 12 racks, just to give some spacing in between. Okay, so this is all about the design of the membrane system which we have. Is it clear? Anything which you cannot understand? Any part of the question? It was a little lengthy problem, but I hope you understood it. Shall I move forward? Okay. Okay, so this is the last subjective problem. It says A 620 liter per day of wastewater sample containing chromium was treated with 2.5 gram per liter of activated carbon, which resulted in 82% of the contaminant after 3 hours of contact time, leading to the final concentration after treatment to 1.5 milligram per liter. Now, based on the information, answer the following question. What is the solid phase concentration of chromium on the activated carbon? So it says that we have wastewater, the flow rate is 620 liter per day. Okay, but it contains some chromium. So to remove that chromium, I have added activated carbon. So it will absorb all the chromium. So per liter of wastewater, I have to add 2.5 gram per liter. Okay, so 2.5 gram per liter of wastewater I have to add. This is the activated carbon concentration. So after adding the activated carbon, it resulted in 82% removal of chromium. How it is getting removed? It is getting absorbed to the activated carbon. So from the water, 82% of the contaminant or chromium is getting removed. So after removal, the final concentration of chromium was 1.5 milligram per liter. So we have to find out the solid phase concentration. So whatever chromium is adsorbed on the activated carbon, I have to find out what is the milligram of chromium adsorbed per gram of activated carbon. Okay. Did you understand the problem? Fine. Okay. So we'll see how to solve this problem. So we have to find the solid phase concentration. So first we know that 82% is removed. That means 18% is still present. So 18% of some initial concentration, let it be C naught, is 1.5 milligram per liter. So my initial concentration of chromium will be 8.33, or I will write it as 8 milligram per liter. Okay, so my initial concentration of chromium is 8 milligram per liter because 18% is removed and 18% after removal it is 1.5. Okay, now again for activated carbon, 2.5 gram of activated carbon is required for 1 liter of wastewater. Okay, or treated water, whatever. So for 620 liter per day of wastewater, my activated carbon requirement will be 2.5 gram into 620 liter per day, which will be equal to 500 1550 gram per day or 1.55 kg per day. Okay, so for 1 day, so for 1 day of my operation, my mass of the adsorbent M, the mass of the adsorbent or the activated carbon is 1550 gram, and the volume of treated water is 620 liters. Okay, so these are all the parameters. Now finally the adsorption capacity, that is the solid phase concentration in the adsorbent. So absorption capacity QE will be equal to, my initial concentration was 8, or I will write the formula for you. It will be C naught minus CE into V by N. Very simple. So it is 8 minus 1.5 into 620 by 1550. So if I solve it, I will get it as 2.6. Okay, so it will be within the 2.6 milligram per gram. So or I can say 2.6 milligram chromium per gram of activated carbon. So this is my solid phase concentration. Is it clear? Any doubt in this? Okay, so it was a very simple problem. Okay, so now we will see some objective problems. So the first question says, typically advanced treatment of wastewater is carried out before biological treatment, during biological treatment, after biological treatment, or after disinfection. Please answer. It's a very simple question. So when do we perform the advanced treatment? Anyone? During biological treatment. Why do you think so, Abdul? Like, why do you want to do the advanced treatment of wastewater during biological treatment?
This is after secondary treatment only it is coming to the advanced treatment. That time also this biological treatment is going on, isn't it?
No,
That's
biological treatment is done in secondary treatment itself.
there itself it is finished.
Yeah, yeah. So after that, we have to do advanced treatment only, the removal of the nutrients or any other recalcitrant organic
Yeah.
pollutant. Okay, so
Yeah,
after,
in that case, it is coming only after biological
after.
treatment. That
So it
yeah,
will
yeah,
be
okay.
after biological
I,
treatment.
yeah, that's right. Because some emergence and all these things is removing from the this advanced treatment.
Yes,
Emergence, just
yes,
like
yes. Okay, so it will be after biological treatment. Now next question, we have to match the following. So we have nitrogen removal, phosphorus removal, and dissolved solids removal. So we have gas stripping, reverse osmosis, and chemical precipitation. So tell me what is the correct match for these. So how do we remove the nitrogen? Which of the following? You don't have any idea? What are the different processes to remove nitrogen? You can at least try. Tell me something, whatever you know. Hello, are you guys there? What are the various processes to remove nitrogen? Have you heard about ammonia stripping? Hello, are you able to hear me?
yeah, yes, sir.
So for nitrogen we use ammonia stripping, right? You know that in wastewater we have like ammonium ion present in the wastewater. So with the help of gas stripping mechanism, we remove all in the form of ammonia. We will increase the pH and it will be removed. Right? So for nitrogen removal, we use gas stripping. For phosphorus removal, it can be easily removed with the help of some chemicals. So it is removed by chemical precipitation. And for dissolved solids removal, we use the reverse osmosis. Okay, so this is the answer. Fine.
Okay, sir.
Huh. Okay. Next question. Pollutants or contaminants that can be removed by advanced tertiary wastewater treatment processes. So, which of the following can be removed by tertiary treatment? Recalcitrant microbes, nutrients, dissolved metals, all of the above.
This D, all of the above.
It is pretty simple, direct question because we can remove all of these with the help of advanced wastewater treatment. So it will be all of the above. Okay. Others, I hope it is fine. Saket, are you able to listen? I'm not. Okay. Fine. Okay. So the next question. Identify the correct statement regarding nitrogen removal from wastewater. So it says typical municipal wastewater effluents majorly contain ammonium nitrogen and organic nitrogen. Next is nitrification. Denitrification can be removed by precipitation of nitrogen. Third, ammonia stripping is a biological method of nitrogen removal. Fourth, for nitrogen removal, nitrification should be carried out in anaerobic environment, while denitrification efficiently occurs in aerobic environment. So which of the following statement is correct?
This is a typical municipal water effluent measure.
Okay, yeah, yeah.
This
So
is A.
yeah, so in wastewater, we will have nitrogen either in the form of ammonium ions or we will have organic nitrogen. So option A is correct. So if you see second option, nitrification, denitrification can be removed by precipitation. So it is not a precipitation of nitrogen. Okay, so nitrogen gas is removed not through precipitation. So B option is incorrect. In C option, it is saying that ammonia stripping is a biological method. It is not a biological method. No microorganisms are involved in it. And the fourth one, it is saying nitrification should be carried in anaerobic. It is not true. For nitrification, oxidation is required. For that, we need oxygen. Okay, so it is in aerobic environment, whereas denitrification is in anaerobic environment. Okay, so option fourth option fourth is also wrong. So correct answer is A. Okay, next question. The conversion of ammonium to nitrate through nitrite represent. So ammonium to nitrate is known as denitrification, nitrification, NMOX, or nitrogen fixation. So tell me, if ammonium to nitrate, what is happening? We have ammonium NH4 plus to nitrate, that is NO3. So from NH4 to NO3, what is happening? Is it oxidation or reduction? It is given in the name itself. So ammonium to nitrate, it is getting nitrified. So it means it is a nitrification process, right? In denitrification, uh,
Nitrification.
it is nitrification, whereas in the case of denitrification, from nitrate to nitrogen gas happens. And in the case of NMOX reaction, what is happening? It's a partial nitrification denitrification. Like not everything is nitrified, it is directly changed to nitrogen gas. Okay. So next question. Which of the following is not an advantage of NMOX process? So four things are given. Which of the following is not an advantage of NMOX process? Oxygen addition can be reduced. No need to supplement organic carbon. Increases CO2 emissions. Excess sludge production is reduced. So which is not an advantage. Others also please try to give the answers. You can write it in chat box. Do you have any idea about the NMOX process? So in NMOX process, everything is not nitrified. After a partial nitrification of itself, it is converted totally into nitrogen gas. Okay, so because of this, my oxygen addition is reduced. There is no need to supplement the organic carbon because for in normal denitrification processes, we have to apply some extra organic carbon because it's a heterotrophic bacteria. And then also, in other processes, much of the sludge is produced, whereas in NMOX process, very less sludge is produced. So ultimately, and it also decreases the CO2 emissions. So option C is correct. Increasing CO2 emission is not an advantage of NMOX process. Okay. Next question. Which of the following is not a method of disinfection? Chlorination, ozonation, UV irradiation, ultrafiltration. So which of the following is not a method of disinfection?
It is the ultrafiltration.
Ultrafiltration. Okay, because others are typical processes of disinfection, whereas ultrafiltration may not disinfect the wastewater. So it is ultrafiltration. Next question. Generation in adsorption and ion exchange refers to regeneration rather. Regeneration in adsorption and ion exchange refers to treating the absorbents to be reused for another cycle, recycling the effluents for another cycle, extracting the retained contaminant in solid phase for metal recovery, electrically recharging the resins or absorbents. So here we are talking about regeneration in adsorption or ion exchange. So what does that mean? What do you mean by regeneration? So why do we regenerate in adsorption or ion exchange? We try to reuse the resin or the absorbent. Okay, we try to reuse it. So for reusing it, what we have to do? We have to treat it, we have to recycle it, we have to extract it, or we have to electrically recharge it. And even
Treating the adsorbents uh, to be
to be reused.
reused for
Yes,
another
another
cycle
cycle.
of
Wastewater treatment. So option A is correct because in the case of regeneration, we treat it again. Treat it. Suppose in the case of ion exchange, we will treat it some with some very uh, high concentration of acid or base. Okay, so that it will be it can be reused again. Recycling of effluents will not help. Neither extracting the solid the contaminants. It is also not true, and electrically recharging is also not right. So we treat the absorbent for with some chemicals or anything. Okay. A potential disadvantage of phosphorus removal by chemical precipitation is. So what is a disadvantage of, we have seen that phosphorus can be easily removed by some chemical precipitation method. So what is the disadvantage of it? Does it require high energy or lower removal efficiency, generation of high volume of sludge, or complex operational process? So what is the disadvantage of chemical precipitation?
Is it the complex operation process?
Do you think chemical precipitation is a complex process? We just have to add the chemicals, right?
Yeah, but some skilled operators and all these things
No,
is
no, no. We have to just timely add some chemicals. That's all. Nothing skill operation is required. And also, since we are using chemicals, there is no need of any other electrical energy. So it is not highly electrical demanding. Or the removal efficiencies are also very good in case of chemical precipitation. That's why we do. So, but because of chemical precipitation, there is a lot of sludge is getting produced because everything is getting precipitated. It is not removed or mineralized in the form of carbon dioxide or whatever. Okay, so there is a large number of sludge that is produced. So this is the major disadvantage of any chemical precipitation process. Any chemical precipitation will have a large amount of sludge. Okay, so this is the option C is correct, that it will produce high volume of sludge. Okay, next question. Which of the following statement is incorrect in terms of absorption process? Both physical and chemical absorption are exothermic in nature. Physical absorption is irreversible while chemical absorption is reversible. The energy generated during chemical absorption is typically higher than the physical absorption. All of the above. So which of the following is incorrect?
Option B.
Option B, yes. Option B is incorrect because physical absorption is a reversible process, whereas chemical absorption is an irreversible process. Because in physical absorption, weak bonds are formed, so it is reversible. Whereas in the chemical absorption, very strong chemical bonds are formed, so it is irreversible. Next question, we have to find the incorrect pair: ion exchange, uncharged organic impurities, carbon absorption, refractory organics, alum flocculation, nitrate and ammonia, both A and C. So which of the following is an incorrect pair? What is the answer? Anybody able to solve it? See, alum flocculation. Does flocculation helps in nitrate removal? It is a method for removing the. Can anyone tell me where do we use alum? Not for nitrate removal, right? And also ion exchange process. It is given as uncharged organic impurities. In ion exchange, there are exchange of ions, anions or cations. Okay, so both option A and C are incorrect. So D is the correct answer, both A and C. Carbon adsorption, it removes the refractory organics by absorbing. Whereas ion exchange for charged organic impurities, because in water it will dissociate. And then in alum flocculation, it is used for phosphate removal. Okay, so option D is correct. Is it fine? I hope you understood that. Next question. Match the following. So we have pressure driven membranes, we have electrical potential gradient driven membrane filtration, and we have temperature gradient driven membrane filtration. So we have to match for each of them. Very simple.
Option B.
Option B. Yes. So reverse osmosis is a pressure driven system, just like any other ultrafiltration or nanofiltration. Then electric potential gradient. So in the name electrolysis, we can directly find it as a electrical potential driven membrane. And finally, distillation is a temperature gradient driven membrane filtration process. So option B is correct. Now the last question, it's a small numerical. It says if a membrane fed with 700 milligram per liter of TDS generates 30% reject with 2200 milligram per liter of TDS, what would be the approximate TDS concentration in the permeate? So flow is coming, 30% is going as reject, so the rest 70% will go in permeate. Okay, so you have to find the concentration of the permeate. What is the right answer? Just it's a one-line problem. Just solve it and tell me. You can simply do mass balance. Is anybody trying, or should I show you the solution? If you are trying, please raise your hand. I will wait for some more time. Okay, we'll see how to solve it. So, as I said, in permeate, 70% is coming. So, zero point 0.7 into x, I don't know the permeate concentration, plus 0.3 into 2200 is equal to the 700. Okay, so if we solve for x, we will get it as 57 milligram per liter. Okay. I hope it is fine. Okay. So those are all the questions that I had for this week. So if you have any doubts regarding the questions we solved or any other doubt, you can ask me now or we can close the session. Any doubts regarding the problems which we solved today? So we will have the next class on 3rd October in the 7 to 9 p.m. slot. And if you have any other queries, you can write to me at saha19akash@gmail.com. Any queries, guys? Or you can leave the session. Okay, thank you, Abdul. Saket, you have any query? You can leave the session if you are done. Thank you, Chinmay. Thank you, Saket.